There is one important point here to clarify regarding the time shift property is that we said that if you have a function f of t with a Laplace transform f of s, then when you shift this function in the time domain, then you multiply by an exponential in the s domain with the same sign. But there is one important note here, is that implicitly when we do the Laplace transform f of t to f of s, we assume that f of t it exists in the positive side, or implicitly it is multiplied by a unit step. So implicitly it's multiplied by a unit step. So when you shift this function, you are shifting f of t by f of t minus t naught, and also you are shifting the unit step to unit step of t minus t naught. In this case, you apply the shift property. But if you shift only the function without shifting the unit step, then this shift property will not work correctly, right? So because again, I will repeat that again, because implicitly any function that we do Laplace transform for, it's implicitly multiplied by unit step. Then when you shift this function, you replace t with t minus t naught, you should replace it in the function and in the unit step. So it should be shifted. The function itself should be shifted and the unit step should be shifted. In this case, you can apply the Laplace transform correctly. But if you shift the function only and you keep the unit step as it is, then you cannot apply the time shift property. For example, if I give you an exponential, let's say exponential minus 0.3t, okay, and I say that its Laplace transform is 1 over s plus a, 1 over s plus 0.3, right? Then if I ask you to find what's the, let's consider two cases, to find what's the Laplace transform of exponential minus 0.3 t minus 2 multiplied by ut minus 2, and another case, find the Laplace transform of exponential minus 0.3 t minus 2, and I just stop like this. I don't write unit step of t minus 2. So implicitly, if I don't write anything here, you assume that this function goes from 0 to infinity. It's multiplied by u of t, right? So there is a difference between these two cases. The difference is here we shifted our function by 2, right? So its Laplace transform would be 1 over s plus 0.3 multiplied by an exponential minus 2s. So we can apply the time shift property here. Why? Because originally our function was multiplied by unit step, and now I replaced every t with t minus 2, so we can apply the time shift property correctly without any problem, and this would be the result. But now if I want to calculate Laplace transform for a function like this function implicitly, if I leave it like this, implicitly it's like exponential multiplied by u of t. Be careful, this function, if you plot it, it starts from 2, right? It's an exponential that starts from 2. But this function, it's an exponential, yes, it's shifted by 2, but it starts from 0. You see the difference? So here we applied that time shift property correctly, but here we cannot just apply the time shift property. What we will have to do is, you take the 2 outside, so you can write this function as, exponential minus 0.3 multiplied by minus 2, so exponential 0.6, okay, multiplied by exponential minus 0.3 t u of t, and then you say that the Laplace transform for this, the Laplace transform for this function is exponential 0.6. This is a constant. You can calculate it using the calculator, and then this function. It's just a regular exponential with a Laplace transform 1 over s plus 0.3. So do you see the difference now between the two cases? Here this is 1 over s plus 0.3 multiplied by exponential 0.6. Here this is 1 over s plus 0.3 multiplied by exponential negative 2s. Big difference between the two cases. So this is just an important a tricky point to notice when you use the time shift property. Okay? In general, we can generalize the time transformation. We can generalize the time transformation in general, and we can say that if you have a function f of t with f of t that has a plus transform f of s, then f of at minus b multiplied by u of at minus b. So here we have a shift and scaling, but here there is a condition that a must be greater than 0 and b also greater than or equal to 0. Why do we have this condition, a greater than 0 and b greater than or equal to 0? Because if a is less than 0, this means that you are going to do time reversal, and the function will be in the negative side, and this is not allowed. Because here in Laplace transform, we consider that the function it exists in the positive side only, right? So it's not allowed to do time reversal here. So that's why we put the condition that a is greater than 0. Same for the shift. Shift must be in the positive side. You shift your function in the positive side. In this case, the scaling will cause that you divide over the absolute value of a and you replace every s with s over a, and the time shift will appear in the s domain as an exponential. So here you can say that first you replace every t with t minus b, so you will get f of s exponential minus bs, right? And then when you scale, you replace t with at, then you divide over a, and then you replace every s with s over a. So this is the general time transformation rule. Okay, and as an example of that time transformation, we are going to solve this example. Find the Laplace transform for delta 5t, unit step of 5t minus 3, ramp of 4t minus 6. So we'll start with delta 5t. Originally the delta t, we found that the Laplace transform is 1. So if you replace t with 5t, what happens is you divide over 5, and then you replace every s with s over 5. Here we don't have s, so we will not replace anything, and the result will be 1 over 5. Another example is u of 5t minus 3. We know that the unit step has a Laplace transform of 1 over s. So we can start with anything. We can start by saying that if we replace t with t minus 3 by the shift, then we get 1 over s multiplied by exponential minus 3s. And then if we replace t with 5t, we'll get u of 5t minus 3. Replacing t with 5t, you divide over 5. You replace every s with s over 5, so this will be s over 5. Okay, and this will be exponential minus 3s over 5. So here 1 over 5 multiplied by s over 5, this will give you 1 over s exponential minus 3s over 5. Okay? You can do it in another way. Here we start with the shift, then scaling. We can do it in another way by saying that if we start by replacing t with 5t, so u of 5t would have a Laplace transform of, you divide over 5 and you replace every s with s over 5, so this will be 1 over s over 5, so this will give you 1 over still 1 over s, and then you replace t with what in order to get u of 5t minus 3. So you should replace t with in order to get u of 5t minus 3, you should replace t with t minus 3 over 5, right? So if you replace t with t minus 3 over 5, you get u of 5 multiplied by t minus 3 over 5, right? And its Laplace transform would be replacing t with t minus 3 over 5 is you multiply in the s domain by exponential minus 3 over 5s, which is exactly the same result. So 1 over s multiplied by exponential minus 3 over 5s. This is also s modified, by the way. Huh? This is s. Okay? Last one is ramp of 4t minus 6. We know that the ramp function, we found it to be, the ramp function, we found it to be 1 over s squared. Okay, if you look at the tables, you'll find that the ramp function it has a Laplace transform of 1 over s squared. Then, now, when you replace t with t minus 6, you get 1 over s squared multiplied by exponential minus 6s. Then if you replace t with 4t, so it will be ramp of 4t minus 6, its Laplace transform will be 1 over s squared, and you replace, first you divide over 4, then you replace every s with s over 4, so this will be s over 4 squared, and this will be minus 6s over 4. Then you work out the math, so this will be s over 16, which will turn out to be 4 over s squared, exponential minus 3 over 2s. So that's it for the example. By the way, the ramp function here, we found it from the tables, but later from the properties we will find that we can obtain it using the integration property from the unit step function. We'll show how to obtain this expression. Okay, we'll see you in the next video.